All right. So today we're going to be talking about some basic mathematical models. So when we're trying to model some kind of situation, there are going to be a couple of steps that we take. So one of the first things that we're going to do is figure out what are we measuring? What are the variables? And how do they depend on each other? So for instance, are we looking at how things change over time? Well, then we'll be taking derivative with respect to time. Are we going to be, does it make sense for us to build the equation in terms of something like concentration, if we're looking at some liquid, or maybe in terms of like amount? This is a process that can take a little bit of practice, and you may have to experiment a little bit. When we begin, we should name the things that we're going to be measuring and tracking. So we'll call things S or X or whatever. We also want to think about what should our units be. We're also going to consider what underlying principles what underlying principles govern our rate of change. Sometimes you'll be told. Other times you may have to figure it out from some like either physics principle or maybe a description. So for example, in some of the examples we're going to see, we'll use things like, well, the rate of change is the rate in minus the rate out, or we might use Newton's law, Newton's second law. Forces, the sum of the forces gives us the mass times acceleration. Okay. We are going to try and translate the underlying principles into our variables. And we are going to check that our units make sense. So for example, if we have units of grams for one part of the problem, and we're trying to add to that units of grams per liter, something's wrong in our setup, right? The units don't add in that way. All right, and then often what we're going to do is look at our model, look at the solutions of our model. Okay, we might look at things like phase or direction fields, slope fields, that is. We might also, if we can solve it, we might solve it and check to see that basic predictions that we might make for the behavior of our solutions are actually satisfied by the solutions we find. Okay, so we're going to go through just a variety of different problems. Starting with an object falling, assuming there's no drag. All right, So we're going to imagine that we have an object that has mass m that's falling to Earth, and like maybe in like a big warehouse where there's a vacuum. So we're not assuming any air resistance. Okay. So as we're setting this up, what we're going to be using is Newton's second law, which says that the sum of the forces, the net force, is going to be given by, is equal to the mass of the object times its acceleration. In this case, we only have one force acting, which is mass, which is the gravity force. The force of gravity is given by mass times the gravity constant. And so this is going to be mass times 9.8. Okay, all right. So our constants here are mass, what are we going to be measuring? There are two ways we could set this up. We could set this up in terms of the velocity of the object. We could also set it up in terms of the position of the object. Here, I'm going to set it up just in terms of the velocity. So our variables are going to be the velocity of the object, which is going to be given in terms of meters per second, and time, which will be given in terms of seconds. Okay. And what we can do here, so we said that the only force acting is the gravity force. So this is 9.8 times the mass, and this is going to be equal to mass. And how can we interpret acceleration in terms of these variables? Well, acceleration is just the derivative of velocity. So this will be dv dt. Okay. Now, notice there's a mass on both sides. And so we just get 9.8 is equal to, dv dt. This is our differential equation. We could add an initial condition asking whether we're just dropping the object at time 0 or whether maybe we're chucking it downwards. So it might have some initial velocity. But this is the basic model, and it's easy enough for us to solve this. What do we find? This tells us that the velocity is going to be equal to 9.8 t plus a constant. Right? And that constant will be what our initial velocity is. Okay. All righty.